So, hello and welcome to our lesson today in theoretical mechanics. So, our lesson today in theoretical mechanics is going to be the answering of some questions in um system of particles. Alright, so the first question is we have to differentiate between holonomic constraints and non-holonomic constraints. Okay, so the question, the answer to the first question. So, holonomic deals with position. That's the most important thing here, or the configuration of a system of particles, and the non-holonomic deals with velocity. In other textbooks or in other sources, you will see that the holonomic deals with position, and they will say the non-holonomic deals with anything other than position. So that means the most important keyword in the definition of the holonomic is position, while this is the velocity or anything which doesn't deal with position as you find in other sources. So let's go to the second question. So the second question says we have to mention the two types of holonomic constraints and explain them. So we have basically two types of holonomic constraints, and they are the rheonomic and the scleronomic. The name is some weird, right? Alright, we are learning sometimes. Alright, so with the rheonomic is a constraint where time is explicitly present in the constraint equation. So the only difference between these two, that's the rheonomic and the scleronomic, is that whilst the rheonomic constraint is where we have time being present explicitly, the scleronomic is a constraint where time is not explicitly present, right? So that's the difference between the two types of constraint in terms of the holonomic constraint. So this is the answer to the second part of the question. Right, so the most important keyword here is that time is explicitly present. Oh, Charlie. Right, so and with the scleronomic, time is not present explicitly. So the third part of the question says that if a 5 kilogram wheel is rotating at 4 rad per second and with radius of gyration 2.5 meters, we have to find the kinetic energy of the wheel. Alright, so extracting some data from our question, we know the mass is 5 kilograms, and this happens to be the angular velocity, which is 4 rad per second, and there's our radius of gyration, which is 2.5 meters. So let's find for the kinetic energy. So you're finding for the kinetic energy or the rotational kinetic energy. So this here is just our data, and the rotational kinetic energy is given by this formula here, half times. So this I here stands for the moment of inertia, and the omega here stands for our angular velocity. So in this question, we know that our moment of inertia I is equal to mr squared, right? So we have our m and we have our r. So we can use that to compute our moment of inertia, and doing that is going to give us 31.25 kilogram meter squared. And when we make the substitution in, you're going to get half times. So now this is our moment of inertia, and this is our um angular velocity. So after making a computation, you're going to get our kinetic energy to be 250 joules. So there is an alternative solution to this question, and I would like us to also go through that. So one thing that you have to know is that our radius of gyration, that's small k or capital K, anything, is equal to the square root of our moment of inertia and the mass, right? So in this case, we've been given the radius of gyration and we have the mass. We're supposed to find for the moment of inertia I. So we have to square both sides. So you are going to get K squared will be equal to T I over M, where I is the moment of inertia. So that means our I will be equal to mk squared. So you see it is quite similar to this, except that here we used R for the k, right? So this will help you to get your I. Then you follow the rest of the procedure as we've already illustrated, and that will help you to get your kinetic energy, which in this case is 250 joules. So the second part of the question, no, the fourth question, sorry. So it says, given a system made up of three particles with masses and positions, so particle A has a mass 1.5 kilograms. Then we have this position, and this for particle 2, this for particle 3. So we can see the mass and the mass and the position for particle 3. So using the inertial tensor, so know that this is the important keyword here, the inertial tensor. We have to find the moment of inertia of the system rotating about an axis 263. Alright, so from the question that we just read, we can gather the following data. So we are naming the three particles, particle X, Y, and Z. So with particle X, this is the mass and this is the position. With particle Y, that's the second particle. This is the mass and this is the position. And with particle Z, the mass, the position. And this happens to be our axis of rotation N. Alright. So we have to use the inertial tensor to find the moment of inertia I. So in terms of the inertial tensor, the moment of inertia I is given by n cap transpose, then I subscript t, then n cap, where n cap in this case is just the unit vector of our axis of rotation. So it's given as n over the magnitude of n. And our it here stands for the inertial tensor, which is computed, which is given by what we have here. So it is equal to, so the sum of the masses of whatever we have here in this matrix form. So as you can see, so this can be reduced to this form. So the mass here, the summation of the mass here times whatever we have here. So sorry, since we have summation here, there is no need for this summation to go through. So it's given us what we have here. So in this case, our ISX is just giving us whatever we have here times the mass. So mi, then yi squared plus zi squared. And so that's how we can find for our ix and the rest. So that means whenever we have this here representing the inertial tensor, we have to compute 9 things, okay? But luckily enough, 3 of them are the same. You know, computing the diagonals, that's ISX, IYY, and IZZ is quite simple. Then when it comes to the rest of the 6 remaining elements, fortunately for us, this is the same as this. This is the same as this, and this is the same as this. So in this case, we can say our inertial tensor is symmetric, right? Since in terms of matrix, then Aij is equal to Aji. So we are supposed to compute 6 things here. We have to compute 9, but 3 of them are the same, so just 6. So this is our axis of rotation n. So recall that in the formula we use n cap. So n cap, as I said, is given us, like, we just have to find the unit vector of our n. Alright, so that is going to give us n over the magnitude of n. So the magnitude of n is computed here to be 7. So that means our n cap is going to be, there's our n over 7, which gives us this particular vector here. So now we are supposed to find the 6 things in the inertial tensor. It's a matrix. Alright, so this is the formula for computing our ISX. So our ISX is equal to this formula we have here, which when you expand it, it will give you m1 times y1 squared plus s1 squared. This will give you m2, this will give you m3. So this is because we had three particles, okay? Three particles. So that means I starting from the first particle to the third particle, right? So in this case, here, come let me show you something here. We name that particle XYZ. You can also name it 1, 2, 3. It doesn't matter. Alright, so our ISX is given by this formula here, which when you expand, you get this as I said. So the only thing for you to do is to make in substitution. So for instance, when you take the first particle, the mass is 1.5. The y part of the coordinate, the position was 2, so 2 squared. The z component was 4, so 4 squared. Then that's the formula we follow to compute our ISX, which gives us 576.5. So our IYY is still giving us this formula here, which when you expand, of course, it's obvious we get this. So what this means is that the first particle, the mass is 1.5, so 1.5 times the s part of it, which is 9 squared, plus the z component of the position, which is 4 squared, plus the mass of the second particle. Then we just go on, so it follows that routine, and that gives us 369.5. Then we also compute our IZZ using this formula you can see here. And then when we expand this formula, we get this, right? So we just have to make substitution from the question, which gives us 554. Then we go to IXY, but as I said, it's the same as IYX. So instead of doing two calculations, you have to just do one, which is given by this formula here. So expanding it gives us this. So you just have to make in substitution. So we know that this is the mass of the first particle, the x component of the position of the first particle, the y component of the position of the first particle, the mass of the second particle, the s component of the position of the second particle, the y component of the position of the second particle, and this is the third one. So computing this gives us 166.5. Then we go on to compute IXZ, which is the same as IZX, which gives us 121. Right? Then we go on to compute our last thing, which is IYZ, which is equal to IZY. So IZY, which is given by this formula here, and computing this gives us 196.5. So now means now since we have our values, so you see this our ISX, this, so these are the values, the series values we computed, and we know these they are the same. So initially we stated that our um inertial tensor is giving us this that we can see here. So making in substitution with the values that we computed here, that means you are going to have this particular 3 by 3 matrix here. Alright. Then recall that before we started solving this question, we said that the moment of inertia is giving us this formula here. So now we have all of them. So we just have to make in substitution. So this is the n cap transpose. Note that we found n cap earlier. And this is the inertial tensor we just found. And it's our n cap 2. Right? So making this vector matrix multiplication is going to give us this particular vector here, and this vector and this vector is going to give us 164.7346939, and in terms of two decimal places we can get 164.73, and the unit for moment of inertia is kilogram meter squared. All right, so this is a solution to the fourth question. Then we have a fifth question which says that we are to define the Lagrangian equation of motion and also define the Hamilton equation of motion. So there is just a slight difference between these two different equations of motion. So the main difference is that the Lagrangian equation of motion consists of n second order equations, and the Hamilton equation of motion consists of 2n first order differential equations. So let's answer the question proper, but that's the main difference between the two equations of motion. So the Lagrangian equation of motion is given by this, as you can see here, and one particular system in which the Lagrangian equation is applied is the simple pendulum. Alright, so I cited that example here. Then we've already write this out. Like I said, the Hamilton equation of motion consists of 2n first order differential equations, and it's given by these two first order differential equations, as you can see. Right, so you realize that with this we have 2n first order ordinary differential equations with the equations here, and with this we have Lagrangian, we have just one, so n second order ordinary differential equation. Note that when you find here, this one is going to give us del square L, so we are going to have a second order differential equation. So thank you very much, and we will come your way yet again with another edition of the questions and answers in theoretical mechanics. All the best.